All right. So in this video, we are going to understand why Bitcoin signatures, right? The transaction signatures, which was originally used in Bitcoin, was inherently malleable. If you are if you are watching this video, I'm going to assume that you know one or two things about Bitcoin in the technical level, and you're somewhat familiar with the elliptic curve cryptography. I'm not going to tell you what elliptic curve cryptography is and how the elliptic curve arithmetic works, like addition, inverses, and all. All those things you can find in the Programming Bitcoin book by Jimmy Song. It's a very good introduction. Okay, there are like two chapters dedicated to, one chapter dedicated to elliptic curves and how it is defined in the real numbers and the arithmetic is done, and the next chapter is about the cryptography scheme that is employed in Bitcoin. So in Bitcoin, Satoshi, when he wrote the code, so he originally used the OpenSSL libraries, right? In the OpenSSL library, so he did not re-implement. Okay, so but in the OpenSSL library, the way the signature was verified was allowed two different signatures to be valid for the same private key public key pair. Let's talk about this abstract signature scheme, right? So in an abstract signature scheme, a signature is usually a pair, which is x comma s. X is considered as a witness, and this s is computed by a function of these factors. Okay, and then it is verified. The original OpenSSL implementation, it was possible to give two different values of yes, for both of which the signature was considered valid. And later the proposals were made to fix this, and of course they partially fixed it. Kind of like partially fixed it in SegWit, since SegWit is a soft fork, right? So it kind of like partially fixed it with some kind of a normalization. Okay, and later in 2018, I believe, 16 or 18, 18, I guess. No, I may be wrong, right? Recently Schnorr, BIP-340 Schnorr signature was introduced, which does not have the inherent malleability that we find in ECDSA. Okay, so why, as a Bitcoiner, why should you care about this? Okay, so remember, we as a responsible Bitcoiners, we verify, we never trust. So just because Peter Buell, I hope I'm pronouncing his name correct, but just because Peter said that I have fixed it, right? I have made this proposal and I have fixed it, doesn't mean that you should believe that in face value. As a responsible Bitcoiner, you have to understand like why the fix is working, and eventually verify it in the code that it is actually working correctly. Okay, directly jumping to the code will be like doesn't it won't make sense unless you understand the mathematical idea behind it. So that's where I'm going to help you today. I'm going to help you the mathematics which allowed the malleability that was originally found in the signature scheme. Before we proceed further, let's agree on these certain definitions, right? So this capital G is a generator. If you want to know what exactly is a generator point, just search for libsecp256k1. Sorry, not libsecp, that's a code. So if you want to look at the specification, search for secp256k1. Okay, you'll be able to find the specification of what is the generator point and what is the prime number n and all those things. For every Bitcoin user, a user can have a Bitcoin user should have at least one key. So one private key they need to hold. So we have a private key and we have a corresponding public key, which is a point on the elliptic curve. So it is computed as a scalar product of d times capital G. And we have a secret nonce, one more secret nonce. Nonce is kind of like a random number, which is like generated using a random number generator, whatever. So, if you are familiar with programming, you would know what. You'd have and you're in Bitcoin, you'd have definitely encountered random number generator in your favorite programming language. So, next is capital R is computed by doing the scalar multiplication with the generator G. Then we have the message, which is not just an array of bytes. With respect to Bitcoin, we are talking about the transaction data. And then finally, we have the sig hash. So I have denoted the sig hash using this variable small z. If you would have paying attention, you'd observe that I have used capital letters for points on the elliptic curve, but a small letters for a simple 256-bit number. A point on an elliptic curve has two coordinates x and y. Each coordinate is a 256-bit number. So take a screenshot of this. If you have photographic memory, then that's awesome. Let's move ahead. Okay, and yeah, how does an abstract signature scheme work? So I have the title is abstract signature scheme because this is how any signature scheme has to work. Okay, at least. So we have this prover and verifier. Okay, so the prover is the one who is creating their transaction and who are providing their signature, and the verifier is the one who verifies that the provided signature is actually correct for that particular transaction or the message. So a signature is a pair, this pair of these numbers x comma y, so x comma yes, and this yes is a function of secret key, public key, generator point, that secret nonce, and the corresponding elliptic curve point, and this sig hash. Okay, out of this, these things are public. P is public, G is public, known to everyone. This K and R are not exactly public. I mean, see, this K should be secret. This R, you can think of it, it's still public. Okay, it's still public information. And the Z is also public because when you are providing the signature, I mean, if you are prover, you will pass both the message and the signature, right? So the verifier will verify that this message actually originates from you. In case of Bitcoin, this transaction originates from the person who holds the keys of all the transaction inputs. So all these things are public information. Only this small d and small k are private information. So the verifier will verify based on the scheme. So this f and g are like abstract functions. So in case of ECDSA, you have a different function, different verification function, and so on. So now brace yourself. We are going to do math. It's going to be scary, but you are a responsible Bitcoiner, so you will stay with this. How does this ECDSA system works? So in the ECDSA system, ES is computed as K inverse into Z plus R into D mod n. This n is the prime number which is used in the SECP256K1. It is also in the standard, so this information is also public. So this K inverse and this D, these are the only things which are private. What is this R, you may ask? As you can remember, right, this capital R, which is computed as the secret nonce into the generator point. This is a point on the elliptic curve, which means it has x and y coordinate. This R is nothing but the x coordinate of this point. We just take the x coordinate, just a simple 256-bit number. These are like 256-bit number addition and multiplication, and you take the modulus of it. For example, if let's take a very simple number, okay, n is equal to 5, which is a very convenient number because it is odd and prime, so it has all the nice properties. So if you try to multiply, let's say 2 times 4 mod 5 will again be mod 5 will be equal to 3, because like 2 times 4 is 8. When you divide 8 by 5, the remainder is 3. So model arithmetic is kind of like a remainder arithmetic. So when you may ask, what is the inverse of this number 4 when we talk about with respect to this mod 5? Inverse of number 4 would be, let's try to experiment. 4 into 2 is 8, so no. 4 into 3 is 12, so no, because the remainder with 5 is still 2. 4 into 4 will be 16, right? So the remainder with 5 is 1. So inverse of 4 is actually 4. Okay, so with respect to mod inverse, I mean arithmetic on 5, the inverse of 4 is 4, because 4 times 4 is 16. Similarly, what will be the inverse of 2? 2 times 8 is 16, but what is 8? 6, sorry, 3. So 2 times 3 is 6. So yeah, the inverse of 2 is 3, the inverse of 3 is 2, and so on. Anyway, let's erase these things. So this is how modular arithmetic works. But since this is a very small number, we can like do it. I mean, calculate the inverses and the multiplication, all those things in our mind. But we are this n that is defined in the SECP26K1 standard is a very, very big number. It's a 256-bit number. It's like so huge, right? So I mean, computing the inverse of a particular number in that prime group is very difficult. So naturally, sorry. So how do they compute it? It's by using Euclidean algorithm. It's called extended Euclidean algorithm. Okay, that's how they compute K inverse, right? So it's a still we are finding the remainder, right? Anyway, I mean, the question is like the number that you multiply with k should be equal to 1. So what is the number that's ID? That's the question that we are asking. That's what we are denoting by the inverse. Anyway, so this is yes, and this is r. The signature will be this pair r comma yes. So this will be the signature pair. So now the role of the verifier. Let me use a different color pen. It's like the verifier. Okay, so the verifier does some stuff. The verifier computes these quantities u1 and u2. U1 is this S inverse into no, this S inverse into Z. U2 will be S inverse into R. Okay, as you know, Z and R are like public information because the prover provided R, and even S is public information because the prover provided this value yes. I mean, S is not actually a signature. The pair R comma S is a signature. Okay, because without with simply S you can't do anything. You can't verify anything. Anyway, so now the verifier computes this capital X. So again, this capital X is going to be a point on the elliptic curve. They are going to do U1 times g plus u2 times this u1 and u2 both are scalar quantities. Of course, we are going to take modular of n. Okay, so any multiplication that I do with numbers, it's going to be taken modulus on n. Okay, and they will verify that. Okay, so this will be, let me just write this out. This is going to be some point in an elliptic curve, this capital X. We are not going to actually like solve this problem. Let's just remember the symbols, right? So okay, let's just remember this symbol capital X. Now this is an elliptic curve point which has two coordinates. So the verifier will take the x coordinate of this point and checks whether if it is equal to this small r. If it is equal, then the signature pair r comma s is considered as a valid signature for the provided message. Okay, so the z actually kind of digests that message. So we are verifying that message, even though I have not explicitly specified the message m here. Z is actually a function of m. Okay, so you're indeed verifying the message. All right. Now, why this scheme is malleable? I'm going to consider another signature pair, which is r comma n minus s. Okay, so usually this s and n minus s, they will never be the same. They will always be the different provided, right? I mean, I'm just assuming that this s, since I take a modulus of on n, right? So in every operation, I mean, even when I compute this s, I have taken the modulus on n. So the s will belong to this range of 0 till n minus 1 inclusive. This is an inclusive bracket. But the s won't be considered as a valid if it is equal to 0. So we exclude 0 as a value. So like, I mean, when the prover is calculating the signature, the prover first calculates this value s and r and then sends it to the verifier, right? So when the prover calculates, if the value of s comes to 0, he will again recompute the signature with a different random number. So random nonce, right? Remember, the small r comes from this secret nonce k. So he will like once again generate a different random number and tries to compute this quantity s again for that particular random number. Okay, why random number is required for signature verification, that could be another YouTube video, right? For now, let's proceed. Alright, so now let's say this is x dash. We are computing a different point because we have this pair n minus s. We will similarly do n minus s inverse z into g plus n minus s inverse r into p. Right? I mean, so the u1, I mean the u1 is n minus s inverse z, but I just written them directly. Okay. Now in modular arithmetic, n minus s is actually equal to minus s mod n. Okay. Why that is the case? Okay, why can we can consider the both of them to be kind of like equal, and we won't say equal, we will say this equal, and that's why you are seeing this 3 lines here, not just a 2 line which is traditionally used for equal to sign. Okay, let's go back to modify one more time. Consider minus 2. Minus 2 into 3 will be equal to minus 6. So when you take mod 5 on this, you will get minus 1. Minus 1 is actually equal to 4, congruent to 4 mod 5. Because in modular arithmetic, the number 5 is considered to be 0. So when you are adding the number 5 to this negative 1, you are getting like the positive 1. So if you do any calculations, this will always, satisfy. So wherever you are using 4 in mod of mod of 5, you replace that 4 with minus 1. At the end, if you complete the calculation, you will always get the same answer. Okay. I mean, this idea is fine for this video, right? So this is not a deep dive on modular arithmetic. I'm just demonstrating that in place of n minus s, you can simply replace minus s, negative s. Okay, and that would still be the same. So if we do that, right, in place of n minus s, I'm just replacing minus s. So if we do that, what do we get? So let's just remove this. Okay, so in place of my n minus s, I'm going to simply write s. So this will be equal to negative s, negative of s inverse zg. Just take the negative sign out, negative of s inverse rp. If we take, if we like take the negative sign out on both of these quantities, we will get negative of capital X. Just imagine that I'm having a very big bracket outside. So this will be plus, right? The negative. Distributive law of addition. It applies for this. It applies for elliptic curve like addition. Okay. So we are getting negative of the point X, elliptic curve point X. The negative of elliptic curve point X, right? So how it is defined? It is defined in this way. So forgive my drawing, but this is the most beautiful thing which I can draw. If we consider this point to be P, negative of P is a vertical line downside. So this is considered as a negative of P. This point is considered as a negative of point P. This is how elliptic curve is defined. Okay, the elliptic curve arithmetic is how defined. So with P and negative of P, so Px will be equal to negative of Px. What I mean by the x coordinate of P will be equal to the negative of x coordinate of P. Similarly, Py will be equal to, will be equal both. X coordinate will be exactly equal. The x coordinate won't change, right? Then y coordinate alone will change on the sign. No. Yeah, this will be equal. The x coordinate will be equal, but the y coordinate will not be equal because the y coordinate of P will not be equal to the y coordinate of negative P. They differ in sign. So if this is like x comma y, this point will be x comma negative y. That's what I'm trying to say. Okay. What we have concluded, this x coordinate of x dash is actually equal to x coordinate of x, which is actually equal to r. If r comma s is a valid signature, and r comma n minus s will also be a valid signature. This is what signature malleability means, and it was inherently found in Bitcoin transactions. In SegWit, it was kind of fixed. SegWit is a soft fork, so it was not an hard implementation. Requirement, but it was fixed. Okay, any Bitcoin node which was using SegWit, the update like malleable transactions, it won't create malleable transactions, but it would still accept malleable transactions if I'm not wrong. Okay, anyway. Now, how does this work with respect to Schnorr signatures? Okay, I'm just going to remove this diagram. If you go to Jimmy Song's book, the diagram will be much clearer. Anyway, Schnorr signature. How does this work? Schnorr signature scheme. Here, S is computed as K, the secret nonce, right? Plus this Z, which is the like sig hash. In with respect to Schnorr scheme, it is like slightly different, but will still works into private key. Compare this with the computation of S in ECDSA. This is like much simpler, but it is still as secure, if not more secure than the ECDSA scheme. Why do I say it is possible to be more secure? Because there is a mathematical proof for the Schnorr signature scheme that it is computationally infeasible to break. There is no such proof for the original ECDSA scheme, which was employed in OpenSSL and eventually in Bitcoin, right? So this Z is, as I said, it was computed differently. It was a hash of this private key, sorry, public key, this number R, and in case of Bitcoin, it's a transaction data. But this is how this Z is computed. It's like slightly different, but the specification is like well defined in BIP 143. Okay, you can go refer BIP 143 for more details on how it is computed. All right. So this is the thing, and the pair which is sent, the signature pair, right? The signature is always a pair, is this capital R comma I. So what is this capital R? Once again, it is a secret nonce into the generator G. Now, what will the verifier do? Okay, so the verifier has this data. The verifier does not know about this secret nonce, right? Nonce random number, secret nonce K, and the secret private key D. But the verifier will know about this capital R and this small s. Okay, the capital R is a public key point. Sorry, it's a point on the elliptic curve, and this yes is this thing that we by computing, right? So I mean, if you add two numbers, right, if you add multiply like two numbers, and if you get the result just by looking at the result, you won't be able to get the original numbers which are added together. Like try like conduct a small thought experiment. Okay, for example, 12 plus 6 is 18. If I just give you the number 18, will you be able to tell correctly like what two numbers I have added together? There are like so many ways 18 could you can add two numbers to get 18. For example, 1 plus 17, 17 plus 1, 2 plus 16, and so on. So this is how the secret key and the secret nonce are kind of like hidden, and that's concept called blinding. Okay, so Schnorr signature scheme is actually uh, a zero knowledge proof protocol. All right, so yeah, anyway, so the verifier, right? So verifier, let's use a different color for the verifier. So what the verifier does is the verifier computes S into G and negative of Z into D into P and checks whether this is equal to this point R. And once again, like all these computations are on mod n. Okay, I have just ignored them. Right? I mean, I have not like written them on the board, but you should keep in mind that all these computations are happening over mod n. So the verifier knows this. Yes, the verifier knows the Z. Okay, so sorry. The verifier won't verify this. The verifier will do this. Yeah, the verifier will compute this S into G minus Z into P is actually equal to R. So what I mean, this why this verification scheme works is pretty simple. All you have to do is just multiply G on both sides. Okay, K into G plus Z into D into G. So D into G is nothing but this capital P. Okay. All right. I have to be careful with my handwriting, but it's not the eraser. K. Okay. This is Z, not 2. So this is the capital R. So this is why this verification works. So the verifier, all he has to do is just multiply this SIGAsh with the public key and negate this quantities and verify it is actually equal to the R provided by the prover. This scheme is not malleable. Why is that? Let's consider a different pair. Okay, the same capital R, but n minus s. Now, what will the verifier do? The verifier will, I mean, according to this verifier, I mean, he doesn't know that, this n minus s is sent as a single number, right? So for us, I have written in this variable form, but it's for like to the verifier just a single number. So this n minus s into G minus Z into P. This is what the verifier does. And the verifier checks if it is going to be equal to R. Now let's just expand this equation. Okay, so we get n into G minus s into G minus Z into P. This n into G is nothing but the identity element I, because n is the order of this elliptic curve group. So this identity element is the point at infinity, right? So if you, once again, I'm referring to the Jimmy Song book, chapter 2. So this is the point at infinity. Okay, it's the identity point, right? So this is how it will get simplified. This will be equal to, since this is identity element, so this will be equal to minus of sg minus of zp, right? If this to be, in order for this to be equal to this, right? So here, let's say this is equation 1. In order for the equation 1 to be equal to this equation 2, okay, this term 1, right? So this term 1, I mean, equation is the entire thing. This term, in order for this term 1 to be equal to this term 2, which condition should satisfy? This minus zp is the same in both the terms, so we essentially need sg to be equal to minus of sg. That would mean sg plus sg to be equal to identity element, right, which is a point at infinity. But this sg is actually a point at the elliptic curve. Every point in the elliptic curve except the identity element has the order n, which is a very big prime number. So has the order n means it is not possible, theoretically not possible, for this condition to hold, because remember, if s ever be equal to 0, that won't be considered as a valid signature. So the prover will never send the pair, right? So the prover will send only if s lies in the valid range, which is greater than 0 in that case, right? So this condition will never hold. Okay, so this original r comma s, right? So this original r comma s, this is the original copy of the signature. This will be the only one which is valid in the Schnorr signature scheme. So this is why Schnorr signature scheme is not malleable, and I have explained why ECDSA scheme was inherently malleable. Hope this helps. If you have any doubt, you can ask in the comments. Okay, let's strive to be a better, responsible Bitcoiner. Right. So thank you for watching this video.